the Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program is an introduction to measurement and gauging. Measurement and gauging are cornerstone activities in all phases of manufacturing, from prototyping to final inspection of manufactured parts. There are many measurable process characteristics in manufacturing. Some include the measurement of time, weight, temperature, pressure, hardness, and the measurement of part dimensions. Part dimensions refer to physical properties of manufactured parts, including the part size and shape, and the size, form, orientation, and location of part features. Part dimensions are gauged using some type of measurement tool. This program focuses on these measurement tools and their application. Historically, measurement systems lacked uniform standards and precision. But with the advent of mass production and interchangeable parts, uniform, widely accepted standards and systems of measurement were developed, significantly improving precision. Today, two systems for linear measurements are most often used: the English system, based on the yard, and the International Metric System, based on the meter. Measurement systems are calibrated to primary standards, which are actual physical objects that provide a common reference for measurement standardization. Effective application of measurements and gauges requires an understanding of certain core concepts, including precision, resolution, accuracy, repeatability, and reproducibility. Precision is the quality of being sharply or clearly defined, or how closely the indicated value matches the true value. The precision of a measurement device is in part a function of its resolution, which is the smallest graduation into which an instrument is divided. For example, a rule marked in 1/2 millimeters has a higher resolution and thus can be more precise than a rule marked in millimeters. Accuracy is defined as the degree to which an indicated value conforms to an acceptable standard value. For example, two tape measures may both have the same resolution or graduation, in this case millimeters. However, if these tape measures are not equally accurate, their differences become more noticeable at greater lengths. Repeatability is the degree of consistency achieved with a measuring device when one person uses it to measure the same dimension several times. Reproducibility is the degree of consistency achieved with a measuring or reference device when used by different people to measure or inspect the same dimensions. To ensure accuracy, shop floor measuring devices are calibrated by comparing them to highly accurate working standards, usually gauge blocks. Gauge blocks are machined and lapped or finished to very flat, highly accurate surfaces. Gauge blocks are produced from hard, stable material, such as chromium carbide steel. Because of their high degree of accuracy, gauge blocks are invaluable in calibrating precision measuring tools, instruments, and gauges. In order to obtain the proper length, blocks of different lengths are rung together. The blocks adhere, as though magnetized, to form a highly accurate stack of blocks. Gauge blocks are produced in several grades or degrees of accuracy, and are also produced with angles to furnish simple and accurate measurement of any angle. In addition to gauge blocks, measurement areas typically utilize surface plates, which are flat planes produced from hard, homogeneous granite. Surface plates hold extremely tight tolerances and are used as a reference surface from which dimensions or other measurements are taken. There is a wide assortment of measurement tools used to verify that manufactured parts meet their design intent. These tools are used to measure inside part diameters, outside diameters, height, depth, part squareness, angles, bevels, thicknesses, tapers, and many other part features. These tools range in complexity from non-graduated measuring tools and gauges to graduated measuring tools and gauges, which are enhanced by incorporating dial indicators and electronic digital readout displays. Additional measurement tools include optical measurement projectors, vision systems, coordinate measurement machines, and others. Non-graduated measuring tools and gauges do not have linear or angular graduations marked on the tool. These tools are generally used to transfer measurements to or from a graduated measuring tool, or as a pass-fail comparison to a standard. The primary types of non-graduated tools and gauges include dividers, calipers, telescope gauges, small hole gauges, squares, straight edges, adjustable parallels, and go-no-go gauges. Dividers have two straight legs with sharp-pointed contacts. Dividers are used for measuring distances between lines or points, for transferring lengths taken from a graduated rule, and for scribing circles or arcs. Calipers are similar to dividers, but the legs are shaped with formed contacts at the ends. They are used for measuring distances and for comparing dimensions. Calipers are available in various types, including outside calipers and inside calipers. Hermaphrodite calipers combine elements of both the divider and caliper. Hermaphrodite calipers may be used for scribing parallel lines from an edge and several other uses. The telescope gauge is a T-shaped tool in which the shaft of the T acts as a handle. The telescope gauge also incorporates telescoping plungers that have hardened radiused ends. Telescope gauges are used for measuring inside diameters. The compressed plungers are placed in a hole and then allowed to expand. The gauge is then locked, withdrawn, and the distance measured. The small hole gauge, as the name implies, is used to measure small holes and shallow slots and recesses. The small hole gauge is similar in design to the telescope gauge, but uses a split ball at the contact end, which is expanded to obtain the measurement. Squares are precision tools used for the measurement of right angles. Squares consist of a base into which a blade is set. This blade may be beveled or non-beveled. Straight edges are flat lengths of tool steel or granite finished to extremely fine tolerances. They are used for scribing straight lines and to check surfaces for straightness. Adjustable parallels are employed widely in layout, gauging, and inspection, and expand into a range of widths. They are commonly used for comparing slot and opening sizes against graduated measuring tools. Go-no-go gauges are used to ensure part features are within proper tolerances. Typical go-no-go gauges have accurately sized ends, one within tolerance called the go end, and one outside of tolerance called the no-go end. For a part to be acceptable, the go end must fit, but the no-go end must not. There are numerous types of standard and custom-made go-no-go gauges used in manufacturing, many incorporating graduated scales. Graduated measuring tools and gauges have either linear or angular graduations as part of the tool, and are available in both English and metric units. There are various types of graduated tools and gauges, including rules, combination squares, calipers, and micrometers. Rules are basic measuring tools from which many other tools have been developed. Rules are made from carbon and stainless steels and are graduated in either English or metric units or both on a single rule. Rules are available in a wide variety of sizes and lengths. Some common rule types include spring-tempered rules, tapered end rules for measuring in small spaces, and rule depth gauges. The basic combination square consists of a hardened steel rule and a movable combination square and miter head with a level and scriber. The rule is guided by a machined slot through the head and secured with a lock bolt. Combination squares are useful for layout and measuring of square and 45-degree miter angles. The addition of a center head provides an easy means of locating the center of cylindrical and square work. Adjustable protractor heads are also available. Graduated calipers are a refinement of the steel rule and make it possible to ensure greater accuracy by contacting edges or points to be measured. The primary types of precision graduated calipers used for measuring and gauging include slide calipers and vernier calipers. Slide calipers have a bar which is usually graduated and a pair of jaws that contact the part. One jaw is fixed and the other moves along the scale. Slide calipers are graduated to read outside surfaces and inside surfaces. Vernier calipers are graduated calipers that incorporate an additional graduated vernier scale for greater precision. Vernier calipers consist of a graduated stationary bar with a fixed jaw and a movable vernier slide assembly that combines a movable jaw, a vernier plate graduated into 50 units, clamping screws, and a fine adjustment nut. Each graduation on the stationary bar represents 1 millimeter. The vernier plate essentially divides 1 millimeter into 50 units, with each graduation representing 2/100ths of a millimeter. These 50 units represent exactly the same distance as 49 units on the stationary bar. Because of this minute difference, when a measurement is taken, only one graduation on the plate will exactly coincide with a graduation on the stationary bar. This intersection is where the fractional portion of a vernier caliper measurement is read. To read the vernier caliper, first indicate the number of millimeters that are between the 0 on the stationary bar and the 0 on the vernier plate. Then, locate where the graduation on the vernier plate exactly coincides with the graduation on the stationary bar, and reading off of the vernier plate, note that number's value in hundredths of a millimeter. Add the vernier plate reading to the number of millimeters counted on the stationary bar for the final measurement. This vernier principle has also been incorporated into various measurement tools, including vernier height gauges and vernier depth gauges. The micrometer combines the double contact of the slide caliper with a precision screw adjustment, achieving even greater accuracy. Most micrometers are composed of a C-shaped frame, a stationary anvil end that contacts one point on the part being measured, an opposed threaded spindle which moves to contact the point on the part feature opposite the anvil, a sleeve containing a graduated scale, a thimble with a graduated scale, which is used to advance or retract the spindle, a locking nut, and sometimes a ratchet stop. Micrometers are produced in various precisions, both in metric and English units. In every case, it is the thread pitch of the spindle screw that makes each type different. The thread pitch is the distance between two adjacent thread crests. In this example, the thread pitch of the micrometer spindle screw is precisely 1/2 millimeter. Each revolution of the thimble moves the micrometer spindle 1/2 millimeter. The micrometer has a reading line on the sleeve. The vertical graduations on the top of the reading line each represent a single millimeter. The vertical graduations below the reading line indicate 1/2 millimeters. The beveled edge of the thimble is graduated into 50 divisions. Since a single revolution of the thimble moves the spindle 1/2 millimeter, each thimble graduation equals 1/50th of 1/2 millimeter, or 1/100th of a millimeter. The thimble is rotated and the spindle advanced until the feature is held between the anvil and the spindle face. To read this micrometer, add the number of millimeters and 1/2 millimeters visible on the sleeve to the number of hundredths of a millimeter indicated by the thimble graduation, which coincides with the reading line on the micrometer sleeve. Micrometers are available in a variety of sizes and styles, including inside micrometers for measuring inside dimensions, micrometer depth gauges, multi-anvil micrometers, disc micrometers, screw thread comparator micrometers, bench micrometers, and many others. Dial indicators and electronic digital readout displays are widely used enhancements for tools to improve the precision of measurement readings. Dial indicators have a contact point which is attached to a spindle or rack. When this spindle or rack is moved, it transmits that movement to a pinion and then through a train of gears. These gears magnify the movement, which is then read off the hand of the dial face of the indicator. One of the most widely used comparative measurement tools using a dial indicator is the dial caliper. To read the dial caliper in this example, first note the last visible millimeter graduation on the caliper's stationary bar. Add this number to the 2/100ths of a millimeter graduation indicated by the dial face hand for the measurement reading. Because the principle of direct reading from a graduated dial face provides both accuracy and speed of reading, the dial indicator has been incorporated into many other types of gauging equipment, including dial depth gauges, dial height gauges, dial indicator hole gauges, dial indicator internal groove gauges, and dial comparators. The electronic digital readout, like the dial indicator, has the advantage of being directly read and is used in many types of gauging equipment, including electronic digital slide calipers, micrometers, depth gauges, height gauges, electronic digital indicators, and electronic internal groove gauges. Electronic digital readout tools reduce interpretation errors that may occur when a graduated scale or a dial indicator is read. They provide instantaneous readings. They have quick conversion to and from English or metric units. They can be zeroed out at any point, provide out-of-tolerance alerts, and can be used for collecting and analyzing data for statistical process control. Some measuring devices work by comparing the physical part with an image or model of the part's design characteristics. These devices include optical measuring projectors, vision systems, and coordinate measuring machines. The optical measuring projector is a non-contact method of graphically displaying and measuring parts that have dimensions and shapes difficult to measure with conventional contact gauging tools. The typical optical measuring projector has a stage where a part is mounted. Additionally, optical measuring projectors have an optical path made up of a light source, condensing lens, magnifying lens, and reflecting mirror to bounce a precisely magnified silhouette profile of the part onto a viewing screen. A second illumination source is used to view the part's surface. Once a part is mounted and viewed, it can be measured by using either fine crosshairs etched onto the viewing screen to enter in coordinates, or by using overlay charts, which are drawn to the correct magnification and placed over the screen to quickly judge the conformance of the part to the specified tolerances. Additionally, many projectors incorporate auto edge detection systems that trigger a coordinate reading when light or dark edges are crossed. In a vision system, part information from visual sensors enables machines to make intelligent decisions regarding the part. Three main industrial applications for vision systems are inspection for gauging, verification, and flaw detection, identification for symbol or object recognition, and machine guidance for object location and tracking. In a typical vision system, a part's image is captured, usually with a video camera, to measure its relevant features. This information is converted into electrical signals, which are then analyzed by a computer. The collected image is compared to predefined criteria, including desired dimensions and allowed tolerances. The image may also be analyzed for defects, such as cracks or scratches. The coordinate measuring machine, or CMM, is an extremely accurate measurement instrument that provides detailed data and documentation of manufactured parts. A typical CMM system consists of 4 elements: a machine frame, usually constructed from a granite or other thermally stable material for securing and supporting the part; a probing system used to collect raw part data; machine controls, when machine motion is motor controlled; and a computer system and software to process and analyze the raw part data. CMMs are designed to move and measure within 3 coordinate axes: the x-axis, which runs from left to right; the y-axis, which runs from the front to the rear of the CMM; and the z-axis, which runs up and down. In most CMM operations, a part is placed anywhere towards the center of the CMM table. Depending on the part size and the type of probe used, the part may also need to be secured to the machine table. Once the part is ready, the CMM's probe is moved, manually or by machine controls, until contact is made with the part. Probes are primarily electronic and use a ruby or sometimes ceramic tip to contact the part. Probes can also be non-contact in nature. Reader heads, traveling on each coordinate axis along built-in measuring scales, transfer data on the machine's position from the probe to the computer interface. This dimensional and geometric data is then calculated, compared, evaluated, and recorded. CMMs are available in a variety of styles and sizes, ranging up to systems that are used to inspect large aircraft components. Let's review the material contained in this videotape. The measurement and gauging of part dimensions is a cornerstone activity in manufacturing. These part dimensions are gauged using measurement tools, which range in complexity from non-graduated measuring tools and gauges to graduated measuring tools and gauges, which are enhanced by incorporating dial indicators and electronic digital readout displays. Additional measurement tools include optical measurement projectors, vision systems, coordinate measuring machines, and others. Non-graduated measuring tools and gauges do not have linear or angular graduations marked on the tool. These tools are generally used to transfer measurements to or from a graduated measuring tool, or as a pass-fail check comparison to a standard. The primary types of non-graduated tools and gauges include dividers, calipers, telescope gauges, small hole gauges, squares, straight edges, adjustable parallels, and go, no-go gauges. Graduated measuring tools and gauges have either linear or angular graduations as part of the tool and are available in both English and metric units. There are various types of graduated tools and gauges, including rules, combination squares, slide calipers, vernier calipers, and micrometers.